النار النعيم صدق الله العظيم.
Jazakallah. So first of all, I welcome all of you and thank you for participating in this international webinar. Especially, I'm thankful to our today guest speaker, Dr. Hussein Yusuf Aziz. Dr. Saab is an assistant professor and head of the civil engineering department at University of Al Mutana, University, Iraq. Dr. Hussein obtained his bachelor degree from University of Kufa in 1998 and his master from University of Technology, Iraq in 2001. Then he worked on many industrial projects, and later on in 2009 he joined to obtain his PhD degree from Southwest Jiaotong University in China. He is currently working as assistant professor and head of civil engineering department, and he has a huge experience of working on soil settlement is his specialty, and he has many research publications, and he worked on many projects. So over to Dr. Hussein Yusuf Aziz for presentation.
Thank you, brother Arshad. Welcome for everyone. بسم الله الرحمن الرحيم والصلاة والسلام على أشرف المرسلين. Okay, brother, starting. Start my lecture. Do you hear me?
Yeah, yes, go ahead, please start.
Okay. The screen is okay. You see the lecture, my PPT, everyone?
Yes, right now it is slide 2 is coming.
Okay, well, I will start. بسم الله الرحمن الرحيم والصلاة والسلام على أشرف المرسلين محمد وعلى آله الطيبين الطاهرين. السلام عليكم ورحمة الله وبركاته. My brothers, hope everyone fine and healthy and keep everyone is good. Thank you, brother Rashad, to introduce myself. I am Assistant Professor Hussein Yusuf Aziz, the head of Civil Engineering Department in Al Muthanna University in Iraq. I am graduated from China at 2013. My brother Rashad, he was my classmate. My lecture today entitled Study the Settlement Behavior of Bridge, Pile Foundation and Deep Soft Soil of High Speed Railway. This project, I will make it like this. This project outline as following. As you know, the main problem in bridge foundation design is the control of the settlement and control of the bearing capacity calculation. In the future time or in the present time, the problem of control of settlement has become the main problem because it is the control issue that we have to make it and check it before we go ahead with our design. Also, there is another problem, or it is the calculation of compressed layer thickness. That means how to calculate the compressed layer thickness. This study focuses on these two issues, is the complement and calculation it, and also the calculation of the compressed layer thickness. All you see here is a sample of a bridge. This bridge is carrying a high-speed railway. Actually, this is constructed in China and carrying high-speed train with a speed about 500 km per hour. You see here, this is the foundation, the pier foundation and the girder of the bridge. This is the construction of the pier that we constructed in the field, and this is the pile cap of foundation. This is the final shape of the bridge and showing the process of finalizing it by putting the girder through the construction steps. This is showing the bearing that is used to carrying out the girder. So we start in our explanation to our work. Actually, this work including field program. And this project is the Beijing-Shanghai
Hello, Brother Hussein. Hello. Hello, Brother Hussein. Are you there?
It seems that he's offline, I'm not sure, but his screen is visible.
Yes, maybe it's just. Let me check on phone.
Dr. Arshad, do you have his direct number?
Yes, I'm contacting you. I'm calling you.
Assalam.
Hello, assalamu alaikum, brother.
I'm sorry, there is a problem with my network. Now I come back.
Okay. Just continue.
I'm
Okay.
sorry.
Okay.
Do you see the screen?
Just share your screen. Okay, it's coming. Yes, it's visible.
It's okay.
Yes, it's
Continue.
okay. Visible. Yes, you can continue.
Okay, I'm sorry again.
It's-
Because
it's okay.
bad connection. Okay, brothers. Actually, this work focusing on field test program of the Beijing Shanghai project. There is a new technique is used in this project. The name of the technique is the level meter with a single point settlement. Level meter with a single point settlement. What does this mean? This means, as you see in this figure, this is a technique which is used in this project. Here we bought liquid liver settlement gauge here above the bile cap, and inside the bile, when we construct it, we put the single point settlement gauge during the construction. As you see, this is the vial, and we bought this single point settlement. What is the benefit of this single point settlement? Actually, this is used to calculate the compression of the soil at this point or at this depth by this tool. And the second one also used to measure the compression at this depth or at this point. Also, this third one and fourth, etc. As we see in this figure, the single point settlement consists of fixed end, which is fixed between the vial and the vial cap, and there is sensor to measure the compression, and the surface rod, which is extracted along this vial, and anchoring end, which reached to the required depth. So this is the settlement void settlement, and liquid level meter, which is working upon the quality of the liquid. This is the technique which used to measure the compression. We see here again, this is the single point settlement. This is the sensor, and this is rod, and here we put the top cap. Actually, we have three liquid level with the same level of liquid. But when the settlement is happened for the bridge, of course, the level of the water will be different. Therefore, we will measure the total settlement. The main concept of calculating the settlement is to calculate the final settlement. The final settlement or the total settlement will be calculated here by the level liquid settlement gauge. This is put it, as we mentioned before, on the top of the vial cap. Therefore, when the vial cap is settled down by the settlement or by the compression, therefore, this device will calculate or measure the total settlement. The total settlement, including the compression, will be here in this position, where in the position of the vial. This is the compression. In addition to the settlement under this position in the compressible area. Therefore, this device is used to measure the total settlement, which is consist of the compression in this position of the single settlement account, and also the settlement under the vial bottom here in the compressed soil area. Therefore, we need to calculate not the total settlement. We need to calculate the value of settlement. Where is the value of settlement? The value of settlement is happened under the vial bottom. Under the vial bottom. Therefore, we have to measure the compression here, which we'll name it the D. D means the compression in this position. Therefore, when we subtract S, S means the total settlement, we mentioned, minus the compression of this position. Therefore, we will calculate the settlement in the compressible area. I hope it will be clear. Here is the level meter. As we see, the level meter consists of three devices. The liquid here is the same level, but we put one of them on the top of the vial cap here, and two other in position that has a zero settlement. That means it is the benchmark with zero settlement. Therefore, when the vial cap or when the vial cap is settled down, therefore the liquid here will be different. At the beginning, the liquid was the same for the three, but when the one of them that is putting on the vial cap of the bridge, when they settle down, therefore the liquid level will be different. Therefore, this difference will calculate the total settlements. As we mentioned before, the total settlement, we named it here S. We should subtract from it D, which means the compression here, to find the settlement under the vial bottom. This is the concept of our work. So this device is used in the monitoring system. As you know, we cannot calculate the settlement by hand or manually. We should use an electronic device to calculate or measure the settlement. Therefore, we use this device, which is named remote monitoring system. This figure shows the settlement liquid level meter. There are two, which we mentioned before. It will be put on 0 point of 0 settlements. And the third one will be put on the surface of the bile cup. This method, as we mentioned here, is used to calculate the settlement in the deep soft soil area. And when the rock layer is difficult to monitor, that means the rock layer is very deep. Therefore, this technique is benefit for this case. The process or the procedure of construction and procedure of the testing. As you know, there is a reinforcement of the bile. This is the reinforcement of the bile. We should put this pipe, which means that it is the settlement point or settlement point. We put this pipe and welding it as we see in this figure. This is the first step. After that, we make it vertically, to put it inside the case of the bile. After that, we fix it inside the bile case. This is the pipe, and we fix it. If we need to elongation it, we put another piece, as we see in this figure. And we after that, this is the pipe only. This rod is mean the single point of settlement. As we mentioned before, this is the single point of settlement. We put it inside the pipe. As we mentioned before, it consists of rod and sensor and fixed point. We put after that the sensor here or in the middle, as we mentioned before, and connect it by wire and remote it and connect it with the remote device like this. After that, we put concrete here to make it stable and not moving, and we take here the wire only and connect the other wires, and this is the device which you use to measure the settlement. This is the level meter. This one is the level meter. As we mentioned before, it will be put it on the bile cup. This is the bile cup. After that, we fix the level meter here and connect the other wires, and then we starting the measuring of the settlement by putting the level meter on the bile cup and putting the other. This is the reference one. This is the reference one which connect with the other level meter, and as we mentioned before, it will be put in position of 0 settlements. This is position of 0 settlements. This is the procedure of the testing. After that overview, we take 2 points or 2 work sites. As we mentioned, this is a project of Beijing Shanghai project. We take 2 sites, 2 work sites. The first one is named DK 124 and the second one DK 152. The work site, the DK 142 consists of 2 pairs, D18 and D19, and the second one consists of 3 F371, 372, 373. What is the difference between them? We see here from this table, as shown here, the design of the bile cups and the number of bile is different. The number of bile here is 12, while number of bile here 8 and 10. The depth of bile also 52, here 50, and maybe 47. The bile diameter 1.25 meter, and here is 1 meter. Bile cup dimension also larger. That means the requirement of the design in DK 124 need more requirements for design. Why? Because the compression stratum here is silt and it is 200 kilopascal, while the compression stratum here is salt clay and more strength because it is 250. Therefore, the requirement is less. And load here is more than of the second one. Here the load about 21 ton here, while here the load is more or less, as we see here. Therefore, the requirement of the design in DK 124 is more and need larger number of pile and larger depth of pile and pile diameter and dimension of the pile cup. The loading condition. The loading condition consists of the construction loading. The construction loading. That means when we calculate the settlements in this project, we don't need to take the live load into consideration. Why? Because the final settlements will final settlement will be get after the final step of the construction. You know, the first step of the construction is to put the piles, then the pile cup. After that, the bear. We start to calculate the settlement at the beginning with the bear, which is on here. After that, when we construct the beam, after that, the secondary dead load, which means the pavement and fence and finishing, etc. This is the total load. This total load means the dead load, not live load. This is will be taken into consideration to calculate the settlements, not the live load. As we see here, DK 124 has 2,109 ton, and the second one like this, the difference between them. The soil parameter, when we study a project, we should take into consideration the soil parameter. Therefore, this table shows the soil parameter of the work site DK 124. We should know the water content, gamma saturated, unit weight, void ratio, the coefficient of permeability, Poisson's ratio, cohesion, and phi, etc. This is the soil parameter which we know and is benefit in our calculation. Field study of compressed layer thickness. Now we will study on compressed layer thickness, starting with DK 124 work sites. We see here DK 124 site consists of single point of settlement. How much or how many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We take 10 points. Why 10 points? Because we should take many depth under the pile bottom. Here we see this one is for 4.5 under the pile bottom, and this 9.5, 0.5, that means is very near from the pile bottom. This is the total depth, starting from the pile cap to this point. Therefore, we should subtract from it the pile depth. That means we will subtract the pile depth from this number. We will get this number, 4.5. This means under the pile bottom. 0.5, 18.5, 2.3. That means we start off 0.5 and ending with how much the larger one or the maximum one is 27.5 under the pile bottom. That means we will take the compression or calculate the settlement with different depth here. This is the point we will take it. Here, this figure shows the pile cup, and this is the piles, and the red or pink circle, which mean this is mean the single points. This is mean the single points settlements gauge. We will put here. That mean this pile cup is consists of 4. And this and pile number 9 and pile number 7 and pile number 4. That means we will put in different position, here and here, in the right and left, under and above, and in the middle, like this. This is for D18. For this also we put here in pile number 9, pile number 7, 6, 5, 12, different position. This is for D19. After that, we will get DK 152. My brother Rashid, everything fine? Go ahead.
Yes, brother, you can continue. Yes. Okay, that's fine.
Because I see only the screen of BBT. Okay. This DK 152 also, the work side. Also, we take different depth under the pile bottom, as we see here. 55, that means when we subtract here from 55, the depth of the pile, we will get 5 meter under the pile bottom and 10 meter. And within the pile bottom, that means the depth of pile is 50. That means 50 minus 50 is 0. This is the pile bottom position. After that, 20.3 under the pile bottom, that means we take different depth under the pile bottom to calculate the compression or settlement under the pile bottom. Why we take under the pile bottom? Because the compressed layer is under the pile bottom. We see here also the second work site, DK152. We see it is the dimension is less of the first one, and how many we use? Three, only three. The first one we use for here 3 because the requirement is less. This is for F371, and this for 372. We use only 2 single point settlements, 2 units of settlement plan. Here we use the 3 because the dimension is more bigger than this 372. This is for 373. DK 150, 124 work sites. Now we will get the result. The result here, as we mentioned before, the location here, the location under the pile bottom 0.5, 2.3, 4.5, and we measure the compression here. The compression, we see the compression is starting at 2.7 and increasing 3.124, 4.41, and become stable here. Stable, and the difference become very less. That means the compression will be become less and less when the depth is increased. When we calculate the average compression, we see here 2.72 here. This is the average. 3, 4, 4.86. That means it's become the difference is very less. The difference between 3.23 and 2.72 is more, and also for 4.28. But for 4.42 and 4.86, the difference has become less. After that, it will be constant for 5, only 5. That means when we use our calculate the compression per meter, compression per meter means how to calculate it. When we divide 2.72 on 0.5, we get 5.73. This number is maintained by subtracting 3.13 minus 2 on 2.3 minus 0.5. That means the difference between these value and between these value, 0.23. That means the compression per meter has become less, reaching to value about or nearly to zero. At this point, we will stop the calculation of settlement. And after that, we consider the settlement in this depth is 0. That means 9.5 is show the thickness of compressed layer thickness. Why? Because after this point, the settlement will be neglected. This figure shows, this one shows the steps of loading and construction. This one, for example, of the bear, and this for girder, and this for secondary loading. And this curve shows the compression for different depth. For example, this one, the blue one for 0.5 under the pile bottom, the settlement will be increased. That's not settlement, but the compression. but we should calculate cumulative between them. Cumulative between them. The settlement will be increased by increasing the depth. Why? Because it means the cumulative between them. That means, for example, 9.5 under the bottom is consist of the total settlement from the beginning of the under bottom to this depth. While when we see this table, we see the compression at 0.5 is more and become less. And this figure, we see the value of settlement here or compression is become more for 9.5. Why? Because this is cumulative of other depth. So we also take this work site DK 124, the same. We see the cumulative of compression increased with the increasing of depth, and we should reach to the final one. This is the final value of settlement for the both beer number 19 and number 18. We see the total settlement here with the construction steps here reach to a value about 7 millimeter, between 6 and 7 millimeter. The value of 7 millimeter in our calculation and according to the standardized and codes, it is reasonable values because the limitation in the Chinese code for this project limit the settlement about 10 to 12 millimeter. We get now the settlement about 7 millimeter. This is good value. And we see the period of time. We start from 0 day to about 450 days. That means about 2 years to get this result. We repeat this procedure for DK 152. The same procedure will be repeated. Here also we will see the compression. The average compression here, or compression per meter at depth 0.5 is about 8.25 millimeter. It will become less or minimized to about 0.09. That means about 0. When we reach to this value, we will stop calculation the thickness. We see that at depth 10 meter under the bile bottom, we will get the 0 settlement. After this depth, the settlement will be neglected. Why? Because its value is very, very small. That means the thickness of the compressed layer for this project or this worksite DK 152 is 10 meter, while the first one DK 124 is 9.5. It's very near. 9.5 and 10 can be considered both of them as 10 meter. Therefore, we can conclude that the thickness of compressed layer thickness is 10 meter. Unfortunately, for this worksite F373, we don't have too many points to calculate the thickness or thickness of compressed layer. Why? Because we start of 3 meter, after that we jump to 21. This is wrong. We should use 3 and 5, 9, like this, 10, reaching to 21. Therefore, we get 3, 1.59, at 21 is 0.05. That means the thickness of compressed layer here is 21, but this is wrong. We should use too many thickness, like 4, 5, up to 10. Of course, if we reach to 10, we will get also value like this. Therefore, this result can be neglected or don't take it into consideration. This figure also shows the result of compression with the different depth, and also this is also the second one. We should take the final one which calculates the value of settlement. Here we see the final one, this one. the final one for a 3-level gauge of F371, F372, F373. We see the final value of the settlement reached about 8 to 9 millimeter. 8 to 9 millimeter. As we mentioned before, the code, the Chinese code limitation for the settlement for this project, especially from 10 to 12 millimeter, we reach here from 8 to 9 millimeter. That means this is okay, and our design is okay, and no problem in our calculation. This is the final values of settlement for the project. For DK124, we said before that the settlement is 7 and 7.1 millimeter, and for DK152 from 8 to 9 millimeter, and this is the final values. The summary for this work, we calculate the thickness of compressed layer for DK124 is 9.5, and the thickness of DK152 is 10. That means it's very near. We can assume it or use it as 10. When we make a comparison between the compressed layer thickness and the dimension of the vial cup, and we divide the HS over B, which means that HS is the thickness of compressed layer thickness on the B, which means the width of the vial cup. We see here is 1.18 and here 2.5. This give us indication that the width of the vial cup, when we design the vial cup, we should use width near of the compressed layer thickness. That means when we calculate the compressed layer thickness, it should be match the width. And when we divide them, should be the result near to 1. Here near to 1, here is more than 1. That means this dimension is wrong and not suitable for our design. And this also higher than of this one. This is more suitable of dimension of the vial cup, that we should use about 9 multiplied by 12. This is a suitable dimension for our design. This give us an indication for design and the selection, the best selection of the dimension of the vial cup. Here also we see we used the codes. In China there are many codes. For example, this code is JGJ 94-2008, and this one, second one, and another code depend on the strain control method. That means there are different code, but they use different method on calculation. The first one and the second one depend on the stress. Third one, we should explain some concept to how to calculate this value. The stress control method here depends on the calculation of the stress. That means when we calculate the settlement, we should reach to a depth about 20% of the total stresses. At this depth, we will stop of calculation. This is named stress control method. Stress control method, we should reach for depth about 2.5%, 2.5% of the total settlement. At this point, we stop the calculation and we consider this point is the point of the calculation of the compressed layer thickness. Here, this figure shows the distribution. We see the stress here is starting with maximum value near the vial bottom or the bottom of the foundation generally. After that, the stresses become less with the depth of the soil. Therefore, The method of stress control method, this one, mentioned we should reach about 20% of the total stresses. That means we see here, we consider this is the total stress. When we reach about value 20%, that means we will stop here at this depth. We start again from the beginning. Here we return to for this table. We calculate the settlement. We calculate the settlement by using this code, and also calculate the thickness of compressed layer thickness. When we use this code, the thickness of compressed layer thickness about 6.59, while we will calculate it in the field 9.5. This 9.5 is the real value. This is the real value. This is the true value. Why? Because it is maintained from the field, and 10 also the real value because we maintain it also from the field. 6.5, that means it is wrong or not accurate. Also 7.3, not accurate because the difference about 70%. This is not accepted. Also the difference about 70, this is also not accepted. This method is not good to calculation. The another method, stress ratio less than 10%. That means what's the difference between this first method and second method? This we reach to about 20% of stresses, and we calculate the thickness of compressed layer. But this method said no, 20% is not good value. We should reach to 10% to calculate the thickness of compressed layer. Therefore, we calculate the thickness here about 9.6. It is very near from 10. And also here it is 11.59, also near from 9.5, and more better than this value. The difference here 122. When we use this method to calculate the compressed layer thickness, we calculate here is about 15. It's very big value. And here is 16, also very big. That means the best method to calculate the compressed layer thickness theoretically is the stress ratio less than and equal 10% according to this code. Stress ratio method of 10% is documented for the formation of the experimental work point of a bridge foundation and appropriate for the condition of the stress control method compression layer thickness. Also, we use the codes to calculate the settlements. We use different code. We use American code AASHTO, and we use different Chinese code like CNSC, TB code, JGJ, and TB code, etc. We see the values of settlement is very high. We measure the settlement in the field about 7 and 9, 8, but here 24. It's very big. 48, too much. 56 millimeter. 59, about 60 millimeter. This is not reasonable. This is not accepted. But we should use correction factor. This correction factor, how to get it? By dividing this value measured from the field on this value measured theoretically, we will get empirical correction factor. This is used to correct our calculation or theoretical calculation. Theoretical calculation also by using the code. The method of determining thickness of compression. Here we will we mentioned this. There are two types of calculation: stress control method, this one, and strain control method when we reach about 20%, and we say also another method when we reach to 10%. This is better. And strain control method depending on the calculation of settlement when we reach about to 0.025 of the total settlement. After that, we will calculate the settlement. That means when we reach to a value is neglectable, of calculation of the settlement, or the settlement is very small, we stop of calculation the settlement. Here we mentioned also the distribution of the stress in this figure. And also we will mention the code used in this study. We use in this study the Ashton code, the American code, the British code also, but we don't mention this result. Chinese code, another Chinese code, and third Chinese code. 3 Chinese code and British code and Ashton code. Therefore, we will see someone may be asking why the theoretical calculation is different from the field calculation. Why we get in theoretical calculation very high value. Why? That means the theoretical is wrong? No, it is not wrong. But the enters that we enter it inside the equations is wrong. How? For example, this value, E. It is the compressed modulus, or combustion modulus. The combustion modulus, which we used in our calculation, is calculated between two stresses, between the stress of about 100 kilopascal to 200 kilopascal. This is suitable, and will get correct answer only for shallow foundation. But when we use deep foundation, this is not correct. This is not helpful. That means we should correct this value. Why? Why we correct this value? Because the value of ES, as we can see in this figure, it will increase by increasing the depth. While we use only fixed value, only ES between 0.1 to 0.2, that means this is wrong. That means ES is increased by increasing the depth here. That means we should make a relationship. Therefore, we propose this equation to calculate the compression modulus. Why? Because the compression modulus is increased by increasing of the depth. That means it is proportional increases. So this is the first thing. Also, we should fix the depth of the layer. Sometimes we use depth of the layer 1 meter, and sometimes we use depth of layer 5 meter. We should take this into consideration in our equation, in our proposed equation. Therefore, we divide this value of Z on H naught, which means the reference depth. In our data here, the thickness of our layers about 2 meter, 1 meter, 3 meter. Therefore, we assume in our calculation now H naught is 1 meter. But when we use another project, for example, the depth or the thickness of the layers about 5 meter, 6 meter, that means the H naught should be increased. So we mentioned that ES is depending on Z. There is another issue. For example, sometimes the compression modulus is increased with depth, but sometimes is become decreased. Why? For example, if here is rock and here is soft soil, rock has compression modulus more than of the clay. That means compression modulus and the small depth is more than depth. That means what? That means there is another issue we should take into consideration in our proposed equation. Which one is the beta? Beta depends on the type of the soil, the soil type. The soil type is also necessary to be taken into consideration to calculate the compression modulus. For example, if the soil tight or hard plastic, cohesive soil, we should take the value of V small. Why? Because here is 1 over B. 1 over B give larger value. 1 over B give larger value. And when the soil becomes soft, more soft, for example here cohesive soil, silt, or soft plastic or flow plastic, we should use more than value of beta for example, here from 8 to 10. 8 to 10 will give us less value. Why? Because it is 1 over beta. You know this is in mathematics. So we take two things into consideration: the depth of the layer and the type of the layer, the type of the soil of the layer to propose our equation. Therefore, we should repeat our calculation. We say it here in our course. The calculation was very different between the real calculation, the 7, and here very high. We will repeat this calculation depending on the new value of the compressed layer thickness. Therefore, we take this into consideration in our calculation, and we take these values here. We should mention also, you see this dot, the blue dots. This is the blue dot. This is ES experimental values. We check this equation with the experimental value of ES. It is nearly matching. You see, the yellow one is matching with the red and green. The red, which means the red and the green, which mean? We mentioned that the blue one is the experimental value. The red is the minimum value, and the green is the maximum value. Why minimum and maximum? Because we see here in the table there is two values, 2.5 to 3.5, 3.5 to 5. That means the value of beta, for example, if we take this layer, we calculate ES for 2.5 and calculate ES for 3.5. Therefore, we will get two values. The first value, or the less value, is the red one, and the larger value is the green one. This is for DK 124, and for DK 152 also we take this result. Also we see the result of our proposed equation is matching with the experimental value. Theoretical results. Now we will check the theoretical results again by using the proposed. Firstly, by calculating the thickness of compressed layer. When you use ES 0.1 to 0.2 and proposed value of ES, we see the value of compressed layer thickness, that 6.5 is the same, the 22 the same, no change. That means the proposed equation for ES is not benefits to calculate the thickness of layer, compressed layer. We will check it again to calculate the settlement. We see the value of settlement using it is turned from 65, for example, in TV code to 7.28. That means it's very good. We get value here very near from the field. In CNS code, it was 24.7. By using the ESZ, it will become 7.24. This is very good also. Also for others, 7.2, 8.1, 6.23, that means the result of the settlement is become very good here. That means this proposed equation is suitable to be used in the calculation of the settlement. We will check this proposed equation by using finite elements program, by using Black's foundation program. As you know, there is a program to calculate the settlement by using the finite elements simulation, which named the Black's program. We take two models, DK 124, and we see this model. The different colors shows the layers of the soil, and here our model, and this is the loading, and this is the mesh of the finite elements. This is the first one, and the second one, we see also the different color shows the layers of the soil here, and this is our project here, and this is the loading, and the mesh is more coarse than the first one. This is more soft. That means the result here is better. We will see. We calculate the result of the total displacement by using Black's foundation. We see here by using ES between 0.1 to 0.2 kilopascal, about 88 millimeter. That is very high. very high. It is not accepted. But by using the proposed equation, the value is 10. It's very near. It is reasonable, 10 millimeter. And also, when we use it for DK152, the value by using ES point 1 to point 2, about 40 millimeter. But here is about 9 millimeter. It is very good value. Also, we will repeat this for other models. Here, 82 millimeter, here 10 millimeter. Very big difference between two values. Now we will reach to conclusion and recommendation. The first conclusion, the bridge file settlement of the experimental work site is far less than the values of standardized calculation. The empirical correction will be used. As we mentioned in this research, that the calculation of the settlement by using the codes theoretically will give us very higher value. Why? Because we say that is the wrong of using the theory. No, but by using the entering, the value that we enter with this equation. Also, we can use empirical correction factor. The limitation on the codes give us the limitation between 0.2 to 1.4. But we see in our calculation, we find value about 0.1. That means the code ranged this value from 0.2 to 1.4. We should say to the code, this 0.2 is not enough. We should make it 0.1. This is only suggestion. Why? Because we find it by calculate the values of calculation. Single point settlements and hydrostatic level, which is the new technique that we explained in the first of this lecture. What is the benefit of this technique? It is used to overcome the difficulties when the base bottom layer cannot be stable anchorage, and the soft soil or rock layer is difficult to monitor. That means this technique is very good for this difficulty. Also, we proposed this equation. This equation is very good and give us and correct for us our theoretical calculation by using the codes. Also correct our calculation by using finite element program Blacksys. When we compare between the codes, we find that the Chinese code, CNS code, is suitable more than our codes. That's right. All of codes gives not correct value, but when we compare between them, that means the best one and to give us the good calculation, that CNS code is better than of other codes. Maybe in one issue, maybe when we compare it with other issue, maybe it's become less benefits. Now we thank you. Recommendation: we should use the formula, the correction formula, to be applied with another site. Maybe this formula only suitable for this site. We should use this formula to another site. Also, the factor beta. Maybe the range of factor beta is not suitable for other project. Maybe we need to increase this the scope of the factor beta. And maybe H naught, maybe selecting the selecting one H naught equal to 1 or another value should be become more judgment. We use more judgment to calculate this value, and we should give a law to calculate it. And I'm sorry for a long time, and thank you all, brothers, and I hope you are interested in my lecture, and good luck for everyone, and assalamu alaikum wa rahmatullahi wa barakatuh.
Thank you, Dr. Hussain, for a nice presentation. Now the floor is open for question and answer. Any question you can ask for Dr. Sir. Students, if you have any question, you can ask. Right. Any question from participants?
Maybe they don't understand what I say. Maybe my English not very good.
No, brother, this was good presentation. Maybe they understand everything. That's why they don't ask question. Okay, if you no question from the participants, then thank you once again. Thank you, Dr. Saab, for your nice presentation. And thank you, participant. So we can, okay, we can end the session here. Once again, thank you all, and Allah Hafiz.
Allah Hafiz, brother. And thank you for all. And we hope to see you, inshallah, with lecture in our university, inshallah.
Inshallah, brother. Inshallah, brother.
Welcome to everyone.